Thanks. So first of all, I'd like to thank the organizers for inviting me here to come talk about galaxy mergers. But I also like to note that they are also the ones who are putting me in between you and lunch. So I'm going to have a really hard time to keep to time and make sure that you're all happy by the end of my talk. Okay, so today I'm going to give you a narrative about how the merger-driven scenario of galaxy evolution from a low-Z observational perspective. I'm going to first have a quick walk down the memory lane, and then I'll basically tell you about what mergers and U-lurks and how they're related to each other, and how that what the role that they play is in galaxy evolution. And then I will highlight a couple of key questions that I'm specifically attacking in mergers, and then also end with some sort of outlook in the field. And you notice that the timeline is not exactly linear, and also I'll say that there are a lot of error bars in those brackets that I just quoted. Okay, so let's get started. In the 1970s, the Tumray brothers have done the then state-of-the-art n-body simulations of these galaxy mergers by exploring the effects of dynamical friction on galaxy mergers and seeing how rapidly they could actually collide and end up being elliptical galaxies. And this method was actually initially met with a lot of skepticisms, but over the years, there are more components being added to it and more particles being added, and so this kind of formed the basis of current-day merger simulations. And over the years, also, that there have been a lot of mounting evidence for non-equilibrium features that could disappear within the age of the galaxies. And so you can see in this NGC 7252, for instance, that there are a lot of asymmetric core features and multiple cores to indicate evidence for mergers. And I really like this series of images because it actually shows exposures that are in increasing exposure times from A through C, and then in D and E, they're both 85 minutes, but then they stretch it differently so that you can see the tidal features a little bit better. And I don't really know how you do stretching in like photographic plates, but that was interesting to me. So then there was a game changer. In 1983, yours truly was conceived, and also there was an IRAS satellite mission that basically was the first infrared all-sky survey, and it discovered a new class of objects that we called luminous and infrared, ultraluminous infrared galaxies. And so these lurks and U-lurks basically emit the bulk of their infrared luminosity in the infrared ranges, and we have the IRAS Revised Bright Galaxy Sample, the RBGS, that's been defined over the years, and we've basically accumulated lots of data to understand how the SED of these galaxies are like, and what that tells us about the physical properties in terms of the stellar masses and dust temperatures. Now, these objects play an important role in the high redshift universe. So you can see from the IRAS data and also since then the ISO and SCUBA data that the luminosity function beyond infrared luminosity of 10 to 11 L sun actually has an upturn with redshift. And also Spitzer surveys later on also shows that these lurks begin to dominate the star formation rate beyond a redshift of 0.7. And so these galaxies actually play a very important role in shaping, the cosmic history since, especially since cosmic dawn and noon. But I think that even though they're rare locally, those are basically the situations where we can actually study the microphysics in detail. And so for the rest of this talk, I'm going to concentrate on the local universe. Okay, so what does this tell us about mergers and U-lurks, and how does all this fit into galaxy evolution? Now, there has been increasing observational evidence that points to how infrared luminosity associates with merger activities, including like optical and infrared imaging surveys that would see a lot of disturbed morphologies in these lurks and U-lurks. If you look at gas kinematics or stellar kinematic studies, they show that the U-lurks, which are red points here, they resemble those of the L-star ellipticals on this fundamental plane, to show that they probably are what turns into those elliptical galaxies. And also there's multi-band observations involving H1 gas, also in mergers, to support this whole theory. Now, so what emerges then is basically this picture of a self-consistent merger-driven scenario of galaxy evolution, where you get gas-rich major mergers that kind of come into gravitational influence of each other, and then they start at delicate dance, interact a few times, and then they collide and form what we call like later stage mergers and post-mergers. And a couple of important things happen here, which is that the gas, not just the stars, but the gas also gets compressed and it forms more stars, and so that the star formation rate in these galaxies will exceed like 10 or 100 times than in normal galaxies. And also, a lot of that gets channeled into the center of the system when it loses angular momentum, and it feeds the central nuclear activity, which could in turn turn on the supermassive black hole in the center and trigger AGNs that can make sure that the system then goes into the quasar phase, etc. And then the other important thing is that dust all this time is getting stirred up, and so you're getting dust that reprocesses the starlight into the infrared, so then these mergers then go through the luminous infrared galaxy phase. And of course, depending on whom you talk to, they can probably go through some sort of quenching mechanisms to remove the gas, suppress star formation in the post-starburst phase, and eventually end up red and dead. Now, this paradigm has since then been substantiated with a lot of observation evidence, as well as a theoretical framework that puts this in the context of about a few gigayears, particularly all these action, where star formation activity as well as black hole growth is it's enhanced. It's actually more like in the giga year and a half or so, and all correlates to these merger stages. And so, is that the end of the story? Well, of course not. That actually brings up a lot more interesting questions, where we're kind of asking about what are the mechanisms that power these central engines, how are the starburst and AGN tied, and how do these U-lurks actually turn into ellipticals, if they do, and how does this merger sequence evolve in terms of like merger rate, looking for binary supermassive black holes, and how does AGN turn on, etc. So let's examine these in a little bit more detail. The starburst AGN connection is a term that we've kind of thrown around for the last couple of decades at least, and it's been a debate. I think it started as like a monster versus babies debate, where the AGN and starburst, the stellar nurseries, are actually competing to contribute to the extreme luminosities we see in these galaxies. And there have been a lot of studies, some that indicate using mid-infrared diagnostic lines to show that maybe starbursts are more dominating energetically. So the green squares here are the region the AGN dominates, the squares are the star formation with the dividing line, and then the red circles here are the U-lurks. So then they might be more favoring the star formation mechanisms. But at the same time, you have to realize that this is a very complicated story. U-lurks may also represent different stages where they could be have different types of U-lurks, where this is their IRS spectrum from the Quest survey, and the differences in the silicate absorption could say that U-lurks go through a kind of evolutionary sequence and eventually mimicking that of quasars. And so all of this is to basically say that it's important to understand the relative contribution of starburst and AGN to these mergers, where if you have differences from the contribution of these two mechanisms, you might go through the quasar phase I kind of just described, or if you have a little bit less AGN contribution because of the dynamic of the system, because of various orbital parameters of the merger, you might potentially, the AGN might not get triggered as much easily, and then it could potentially evolve into something else. And so it is also important then to understand the feedback and how all of this gets quenched to look at how the galaxies evolve. And so there had been a lot of also studies then to look for specifically what quenches the star formations. We have seen a lot of powerful winds being detected across the wavebands, and we see specifically merger-driven shocks and winds that are prevalent among these lurks and U-lurks, and it seems to support the quasar mode of feedback in quenching star formation. So here's an example of Macquarie 231, which is a bona fide QSO among the U-lurks, and this is a Gemini cube, I think, a GMOS IFU cube, which really shows the velocity of the neutral gas and the wind that's coming out of the quasar in this direction. So, and of course, if you follow this story, you would expect there to be stages in this galaxy system where it might feature binary supermassive black holes. If you have a black hole in each galaxy and then they merge. And so it's important then to understand the timescales of when these things actually take place. So we sort of see that the lurk to U-lurk transition, if following the merger sequence, might take place over a few hundred million years. And if you understand that the sequence is such that you merge first the dark matter halo, then the galaxy, and then the black holes, then you might expect to see a lot of binary supermassive black hole, or even a triggering of AGN pairs in the late stage mergers. And actually, that's often hard to find. And the reason is because these dual AGNs, they often occur in late stage mergers with very small separations that are often below the resolution limit of large surveys. And we don't really understand exactly the synchronization of the accretion, the triggering of the AGN. And so a lot of this then, is still being under active areas of research. And of course, the recent buzz from the gravitational wave observations will get us excited about merging supermassive black holes. So LIGO is more sensitive to the coalescence of neutron stars and stellar mass black holes, but its successor, LISA in space, is going to be sensitive to the coalescence of supermassive black holes that are more in the range of the masses that I'll be talking about. So really, to understand all this, we need to understand the small-scale environments in which these coalescing black holes are being posed. So thankfully, we live in an era of spatially resolved studies where we have lots of good instruments that allows us to see into these things these processes in detail. So for instance, in the X-ray in Chandra, it actually has a resolution where we can a lot of times spot these dual AGN and dual supermassive black holes. And in the infrared and optical, of course, there's HST, but I'm mostly going to talk about ground-based adaptive optics via KEC, which actually allows us to probe comparable, if not better, spatial resolution. And then in the submillimeter and radio, of course, ALMA and JVLA have been game changers as well, with very good resolution that's basically matching what we're seeing in the optical and infrared. And geez, wouldn't it be great if we have something that can allow us to also resolve things in the mid-infrared? But I'll come back to that at the end. So so now I want to kind of highlight a couple of the key questions that I've been working on mostly. So it's apparent that we should consider both AGN and the stellar components in how they evolve as the galaxy system sequence actually progresses. And so they interact with each other mostly via feeding and feedback mechanisms where the galaxy supplies gas into growing the supermassive black hole in the center, and possibly triggering its accretion, and also which then in turn interacts with the interstellar medium via feedback mechanisms. And it's important, let me illustrate in another simple but not as simple cartoon. It's important to understand the role that gas plays in this galactic ecosystem. And so you have your giant molecular clouds and ISM, and then they go through, they collapse to form stars and go through some sort of stellar evolution, and then somehow that produce winds, injecting momentum into the ISM, and then that could potentially cool the gas and feeds back into your original gas reservoir, or some of that might get triggered into the center, as I described earlier, and that could drive even more powerful outflows and potentially expel and then the gas and quench star formation. And so, given that the gas flows in this whole system, it's so vital to understanding how galaxies may evolve, then we ask some big picture questions regarding feeding and feedback from the observational point of view. So we don't really understand to some degree how gas fueling actually works in terms of feeding the central nuclear activity. Like, there are questions in terms of how supermassive black hole grow, how quickly do they grow, when is the mass accumulated, that we don't know for sure, and how big do they get before they coalesce. And on the other hand, when the gas is being injected back into the ISM, where it actually ends up in small scales is going to be important in affecting how we think about star formation and the merger's role in all this. So, current state-of-the-art simulations now incorporate feedback models into their simulations. For instance, the feedback in realistic environment, or the fire simulations. Here for galaxy mergers, I'm showing on the left is a mock optical observation of the stars, and on the right is the surface density and temperature of the gas of a two progenitor galaxy merging. And you can see that a lot of times the gas, unlike the stars, is actually kind of gets spewed out throughout the process, and not just at the very end when the nuclei finally coalesce. Now, I won't claim to be an expert on simulations, but there are a lot of parameters, free parameters, and subgrid model physics that go into these simulations that we don't really understand. And so what we really want then are observations with these similarly GMC size spatial resolution that could help us compare to simulations and actually constrain the physics. And so in particular, we want to be able to probe the multi-phase structure of the ISM, as well as looking at the properties of these AGN and Cerberus-driven outflows. So to this end, we've been conducting an ongoing Keck-Osiris AO Lurk analysis survey, where our goal is to really study the nuclear star dynamics in a statistical sample of galaxy mergers, so that we can piece together what actually happens as the black hole grows and feeds back as a function of the merger sequence. And so this has been an ongoing survey. We've had a lot of observing time using the OSIRIS instrument, which is a near-infrared IFU as assisted by AO on Keck. And we have targeted so far about 20-some systems, about almost 30 nuclei, and where we're looking at mostly these local galaxy mergers at about a redshift of 0.03 or 130 megaparsec. And here I am showing a subset of 20 of them, and these are ranked in increasing infrared luminosities. The last 6 are U-Lurks. And so you can see that they do span a range of merger stages, from the widely separated binaries all the way to things that share common envelope, and eventually completely coalesced systems. And so what you may also be able to see are these black boxes that actually shows the field of view of OSIRIS. So they're tiny, but we are focusing on mostly the nuclear aspect. And typically we look at the K-band spectrum of Lurks and U-Lurks, and so this is what it looks like. We're targeting the different transitions of the molecular hydrogen lines, as well as the bracket gamma and bracket delta lines. That gives us the hydrogen recombination lines, and also the helium-1. And in some cases, we also see the highly ionized silicon-6 line as a coronal line. And for the lowest redshift systems, we can sometimes probe the stellar kinematics using the CO bandhead. So let me start off with a case study to show you what the data looks like and what we can learn from it. And so I think everyone has a favorite Euler. This is mine, McCarran 273, and it is a late-stage merger, as you can tell from the big tidal debris, but seemingly just one envelope and in the body. But it is a interesting system because it actually features multiple clumps in the center with at least one AGN from X-ray observations. And so what does the OSIRIS data actually look like? Well, this is what it looks like in the center. And this is actually a collapsed K-band data cube of this galaxy, where I'll tell you now that it looks like a multiple dual nuclei system, but actually there have been a lot of multi-wavelength data that shows basically this is the hard X-ray AGN in this compact region, but here there might be some ambiguity in terms of whether it's a radio supercluster of radio supernovae or potentially other things. So here then is the spatially resolved spectra of three particular regions that I've marked in this field of view of OSIRIS, north, southwest, and southeast. And immediately you see that they feature different line ratios as well as continuum in the K-band. And again, silicon-6 actually detected in a couple of these spots. And so you might wonder why I actually highlighted this southeast region. And it may be more apparent when I show you what the iron 2 line looks like, which is actually an H-band, so I cheated a little bit here. But for this galaxy, we had H-band data, which allows us to map the iron 2, which is a shock indicator from either AGNs or supernova remnants. And immediately you see that in the flux map, the iron 2 is actually brightest in this southeast region that I've marked. The contours are from the H-band continuum. And but what's really interesting is if you look at the velocity map, you see this classic rotation curve. And the signature actually was a little bit of a surprise to us initially because we looked at these systems, which are train racks and the macro scales, but we actually do see orderly rotating disks in the center in this and also in most of our other systems. And so we were able to characterize the nuclear disks in all of these merger systems. And also, what's interesting about this sort of rotating signature is that it allows us a direct way to measure dynamically the black hole mass in this part of the galaxy. And so, because we have the spatial resolution to resolve within this black hole sphere of influence, we can then measure at least dynamically the mass enclosed. And so here's I'm just modeling what the observed data, the velocity field is, and we were able to derive a black hole mass of 1.1 times 10 to the 9 solar masses. And now people sometimes don't really trust black hole masses measurements from ionized gas, but we actually have, for this particular galaxy, there was also a black hole mass measurement from OH Maser, which is sort of a golden standard for measuring black hole masses, and it's a pretty close estimate of the black hole mass. So we were pretty confident in our black hole mass measurements. Now, what this allows us to do, however, is more importantly, is to actually answer the question that I first posted earlier in this part of the talk, where if we wanted to understand how supermassive black holes grow, we might want to think about this very tight scaling relations between the black hole mass and the galaxy's bulge property. So this is the well-known M sigma relation, where it basically suggests that the larger the galactic bulge, the larger the black hole mass. But of course, there are a lot of things to think about in terms of the selection and the samples that we're dealing with. But the question that we're interested in asking is actually how do they grow? If black holes grow inside these mergers, do they actually grow linearly, or is it a case where the black holes grow first and then the stellar bulge catch up, or vice versa? And so when we put our galaxy mergers on this plot, we found that they actually lie on top of or above the scaling relations. And so this seems to suggest, well, it suggests a few things, but the simplest suggestion is that maybe supermassive black holes growth actually takes place early on in mergers. And this would be because we have a lot of gas in our gas-rich mergers that could really well and very easily funnel into the center of the system. And like I said, there are some caveats with the system, with this plot that I'm happy to go into if you're interested. But let me then switch gears a little bit and think about, in terms of feedback and how this gas actually ends up and how it would subsequently affect star formation. So going back to Macquarie 273, here is what the data looks like for when I pull out a slice corresponding to molecular hydrogen. And so here again is the flux map for molecular hydrogen. This time you can see that it's actually concentrated in the northern part with a bridge to that southeast clump that I showed you earlier. And we see a similar rotation scale in the velocity map. But what's really interesting here is the dispersion that corresponds to molecular hydrogen, where it's enhanced along the minor axis of the rotating disk. And so what we were able to paint for this system is a picture where we see rotating gas disks around the northern nucleus, and we see direct evidence for biconical molecular outflow coming out of it with some pockets of ionized gas in this disk. And so this is really exciting, being that we're able to see kind of like the smoking gun signature of some of those outflows, the galactic scale outflows that I've alluded to earlier. And we can also, using our data, to quantify these outflow properties, such as the velocity, the masses, the age of the outflow, and also its energy. And so these are direct quantitative results, in this case, that we can compare to the fire simulations to help constrain feedback physics. And that's really exciting for one system, but we want to try to basically look for these sort of outflow in the rest of our sample as well. And we also utilize a couple of other methods where we look for non-Keplerian motion in the gas by subtracting, that rotating gas velocity that we see in most of the systems and subtracting that from the velocity of the gas. So then anything that's kind of not neutral here, i.e. the blue stuff coming out, is basically signifying non-Keplerian motion of the gas. And we can also see some shocked molecular hydrogen in this same system, 3-35, where the H2 over bracket gamma ratio basically tells us where the shocked molecular hydrogen is. And so with this method, we kind of see about in our 20-some objects so far, we've detected maybe 4 really good cases of shocked outflows coming out of the center, and maybe a few more good candidates that we're going to do more follow-up observations on. But let me step back and actually try to answer, the bigger, the more fundamental question that I posed in the beginning, which is how feedback actually affects the nuclear star formation. So here I'm showing nuclear star formation rate as computed from bracket gamma luminosities against a few parameters: infrared luminosity, merger stage, shock excited molecular hydrogen, and turbulent molecular hydrogen. And here now all of the gray points, the underlying points, are integrated values for each system in our sample. And then the color points are the binned points. So I like to draw your eyes to, for instance, the merger class, where we've roughly divided it based on visual classification, where going from like widely separated binaries all the way to late-stage mergers. And so what we see then is actually enhancement in the nuclear star formation rate at these late-stage merger. Now, we are a lot more complete actually in this stage than we are in the earlier stages. So, we might be seeing different trends once our sample grows larger, but it is telling to say that the nuclear star formation rate actually doesn't get enhanced until the very late end of the merger. And if we actually put these in more realistic time scale, then we might be able to pinpoint this very well. And the other thing I like to draw your attention to is this plot right here, where the star formation rate is actually enhanced for the more turbulent of the molecular gas. And so this is basically a signature of positive feedback rather than negative feedback, where gas gets removed and suppresses star formation. And you're just saying that at these small scales, and remember we're looking at the very center of the galaxies, that the outflows is being driven into the ISM, and it compresses the molecular gas, and that actually helps to form stars. And this has actually been seen in like other nearby radio galaxies as well. But this is great. It helps us answer a couple of the questions that I first posted about how supermassive black holes grow rapidly in gas-rich mergers, and also that nuclear star formation rate is enhanced in like these late-stage mergers as caused by turbulent gas. But what's really exciting is that we have this data set that allows us to resolve gas dynamics at the tens of parsec resolution systematically within the kiloparsec region in galaxy mergers. So in the last few minutes, I just want to talk a little bit about what we can expect to see in the next decade or so with upcoming facilities. So JWST, of course, it's an awesome instrument, not just because it has mid-infrared instruments that can resolve anything, but also it's going to have unparalleled sensitivity in the infrared. So comparing, for instance, to CAC at 2 micron or Spitzer beyond 10 micron, is going to have an order of magnitude or two improvement in sensitivity in this wavelength regime. And it's and also this is obviously the first time that we are not just having resolution, spatial resolution in the mid-infrared, but also we're putting an IFU in space. So I'm pretty excited about that. But what it can really do for us is to be able to resolve the mid-infrared. So to visualize, here is one of our LERCs, 2Zwicky 96, and it's a very interesting looking system with at least 2 galaxies merging. And over here on green is plotted its IRS spectrum with the deep silicate absorptions and pH features, et cetera, et cetera. But all of this actually comes from one big slit. And so, JWST, or MIRI in particular, is going to be able to piece apart, what actually contributed to the various pH features or neon lines within this field of view of the galaxy, and so that we can see for the first time, the structure and dynamics of the dust, and also the cooler molecular gas compared to what we were looking at with Keck in the nuclear environment at these small scales. And you might wonder why I actually, have the box drawn over here in this system, and that's because in this galaxy, when we look at the HST NICMOS images, as well as the Keck data with molecular hydrogen and bracket gamma, and actually most of the infrared luminosity is coming from this seemingly off-centered nucleus. So, it might be hypothesized that this is could be a third system that was taking place in this merger, or maybe it's something else. But I think JWST is going to be, making very cool discoveries when we look at the very obscured regions that we couldn't really reach before, particularly to trace, the sort of shock chemistry that I've been talking about, and also to be able to identify AGNs in obscured AGN candidates that can allow us to better pinpoint, when supermassive black holes actually accretion gets triggered and when AGNs turn on at these systems. And of course, if we really want to trace the evolution of how black hole masses get built up, we also might have to go to a little bit smaller mass range to see when they get from the seeds to how large they are today. But current technological capabilities actually won't let us spatially resolve and therefore measure dynamically the black hole masses beyond the local universe. And so the next generation of 30-meter class telescopes could help push these limits. And so I hope that you will forgive me for putting a picture of TMT up here, given my biographical background and also my current involvements with the instrument and various science teams. But I will mention that one of the things I'm really excited about in terms of the 30-meter class telescopes is that if you look at these radius of influence or black hole mass plotted against the distance and also the various resolution limit of what is typical now for IFU observations, as well as for what it will be available to us on one of the first light instruments on TMT, IRIS, is that we can actually really push down to the mass range that we cannot probe to right now, even within the local universe, or we can extend this to higher redshift studies. And so I think there's a lot of promise to be held in this area. Now, something that's a topic that's sort of near to my heart is thinking about not just black holes in the tens of parsec scale in the galaxy environment, but also its immediate vicinity. And so if you want to look at down to the, for instance, broadline region accretion disk area of the black hole, you cannot basically spatially resolve this right now, but you can do that with reverberation mapping, which is a time domain technique that allows you to directly probe the gas physics within the 0.1 parsec region of AGNs by listening to light echoes. I won't have time to go more into this, but I will just quickly advertise that we have led a recent new campaign of the Lake AGN Monitoring Project, where our program was approved for 100 nights, and it took place over the last year or so on a 3-meter Shane telescope at Lake Observatory, and it was the single largest program to be approved at Lake. And so we've got a lot of really good data to basically measure the spectral line variation in order to probe the broadline region gas physics around AGNs. So I think then I will just sum up with my summary slide. So hopefully you are now more familiar with the narrative that I walked you through in terms of how mergers and ULERCs, they all connect and the role that they play in terms of in galaxy evolution. So I'll stop there. Thank you.
So I wonder, why do you think the supermassive black hole is growing effectively at the late stage of merger? So what's the say black hole accretion rate for your ULERC sample?
So let me try to. You're asking sort of when these black holes grow into this region?
Yeah.
So this is actually initial results from the earlier part of our observation campaign. So these are actually all mostly late stage mergers, and we're now and obviously, like I said, there's some caveats in terms of on the location of these points on this plot, but the simple answer is that by, for instance, Macquarie 273, which is the brown point right here, which you might see, oh, why is it below the M-sigma relation? It's actually just one nucleus. This is only the northern nucleus. And so by at least the Macquarie 273 stage, which you can see has already gotten into the advanced merging stage that it is in, it's already in like the 10 to the 9 range. So the mass buildup actually happened before then. And so right now we're basically completing looking at the earlier stage mergers in our observing campaign to better answer that question of yours about whether exact time scale happens.
The last thing you can do is considering the duty cycle and using the 18 to north. For example, the MRK 273 is accretion rate is like 21 thermometers per year, and but the Bell mass measure 10 to the 9. So the growth time scale is Hubble time. So what do you think is it can grow effectively? I mean, for other users, there might be not 18. The growth is very ineffective.
What do you mean?
So the e-folding time is the Hubble time, so it's very ineffective. Right. So it's quite in contradiction with what you said. So that in the modular process, the black holes and the galaxies they build up together. So it seems to me the black hole is not building up quickly.
It's not building up quickly.
Right. You just calculate time scale. It's very simple.
Maybe this is the question you guys can keep. Other questions? Go on.
Yes, so I have a question on one of your earlier questions. How does the black hole grow? Yeah. So even if you have a merger, you have shocks, you have torques on large scale, you take the gas on tens of kiloparsec scale, you can very easily get it through these mechanisms down to perhaps 100 parsec, tens of parsec, but the gas will stall. And then you need a bunch of different mechanisms that have been suggested. You could have nuclear bars, you could have dynamical friction, you could have stellar feedback, you could have viscosity. And it seems to me the data you have is very powerful to look at these. I mean, you've already indicated signs of stellar feedback. But for instance, you see the disk, right? Have you tried to either look at your Keck image to see if you have evidence of asymmetries, m equals to 2, so nuclear spirals or nuclear bars? You could also do that for your kinematics, right? If you subtract it, you will get the S-shaped kinematic that suggests there's a bar. You also showed clumps. So you could calculate the dynamical friction time scale that would give you the gas accretion rate, which would then relate to the question of how fast do these black holes grow. So are you looking into these? And beyond the stellar feedback, can you tell us, if you have looked already, which of these mechanisms do you think is at play?
So the short answer is that yes, we've looked briefly when we looked at basically the gas across our existing sample, at least at the time, and there are indeed like several clumps. There are a few that has the spiral bars and things, but we haven't actually done the calculation on the kinematics of that gas going into the galaxy, because there's just a lot to do with the data, and so that wasn't one of the things that we had attacked so far. Right. But that's definitely something that we would be doing, once we have some of our initial papers out, and then. And
I think your data set would be the best to do that. It's one of the big unresolved problems. How do you remove angular momentum below 10 parsec?
Exactly.
Yeah.
I have a question here. I want to encourage Professor said that you have very good data. That sounds really exciting. And I have a question. When you were talking about star formation, are you also evaluating the external star formation, or are you only concentrating on how these probable black holes are influencing the star formation?
So based on this data set, we can only talk about things that we see, within this. But we do have ongoing observations with larger scale optical IFU data. So with WIFE's instrument from the ANU telescope, as well as CWI on Palomar, and we're hoping to get KCWI time as well, so that we can actually connect the large scale to the small scale. And actually, we have done that for one of the systems, IRAS 1720, and it's a ULERC, and what we see is that from the large scale, we see shocks that are coming kind of from the center of the system, but because of large scale IFU only puts everything into one pixel, and then we actually were able to resolve then that pixel for at least the spatial coincidence of that large scale outflow to be driven from the outflow that we do see within our OSIRIS data. So we have one system published on that kind of science, and then we are hoping to collect more.
Okay, there's one more question. Okay. Last question. When you compare your black hole and budget measurements to the black hole budget relation, how well are actually your budgets defined?
Excellent question. So we, like I said, right now our data set is confined to our field of view of OSIRIS, which is tiny. And so a lot of our X-axis measurements that come from what we try to find as systematic samples of how people have measured it. So there are probably quite a bit of some uncertainty in terms of what this drives. Now, there are two ways that we're resolving this. One is that we actually also put this, these measurements on relation as well as ML relations, and then we basically see more or less the same trend. So that gives us some confidence. And then, once we have a lot of our own large-scale IFU data, then we'll be hoping to measure this more systematically for our systems. Now, there's also another caveat, which is that for mergers, measuring this velocity dispersion is, as you can imagine, very messy. How do you define the the center of the approach? And I think there's simulations that actually shows the sigma kind of going like up and down throughout the merger. So then that's also another complication to this measurement.
Okay, I think that concludes this session. Thanks again to Vivian.